So we will continue talking about selected topics related to estuary and hydrodynamics. And this is a topic that's of interest for everybody who works on estuaries. If you work with a biologist or a chemist, that's the first question they want to find out about the system. What is the residence time of the system? Or at least that's a very frequent question that I get. And it's a very simple question, but it doesn't have an easy answer. But you might say it's relatively straightforward. Like what do you understand for residence time? Does anybody have a concept of what residence time means for an estuary, for example? How would you define it?
The time a certain substance stays in a system.
Yes, that's right. At time a certain substance stays in the system. That's a good way of defining it. Does anybody else have an alternative definition? Or do we all agree that that's a...
The time it takes a particle of water from entering the estuary to leave the estuary?
That's right. It's similar, right? So what was the difference? For a time a particle of water?
Once it enters the estuary to leave the estuary.
Once it enters the estuary, how long does it take to leave the estuary? Okay, so this is some slight difference, right? Anybody else? Anything else? Well, as you see that, I think you agree that that's a relatively straightforward concept, but as we will see, there are different definitions, and it depends on how you define it. You'll get a different answer, and it's not an easy. By the end of this lecture, you'll realize that you can give an easy answer, but you might not be convinced by it, even though you give the answer. Okay, so one way of calculating residence time, or one way of defining it, is the time that requires, or the time required to replace the volume of the basin. V is the volume of the basin in cubic meters, or in length cubed, by the volume influx into the basin. So if we have this situation in which we have a longitudinal section in a generic estuary where you have river discharge coming in at the head, and then that water will tend to go out at the surface, and then you have oceanic water coming in. So in essence, this definition looks at how long it takes for this volume inflow to replace the entire water volume in that basin. So is there an easy way of determining that value? No? Well, it isn't, right? It isn't easy, but it is at the same time. If you use those budgets, you use a bulk water budget, where we say that the volume of water going out equals the sum of the volume of water coming in, so the river discharge plus the volume in equals the volume out. That's a conservation of mass, right? Remember, in bulk form. And the salt conservation would be the salt flux through here must be equal to the salt flux through here. Salt flux in equals salt flux out. That's what it says here. So all we need to know, what do we need to know to solve these two equations with two unknowns? Go to middle school. But what variables do we need to know from?
Salinity.
That's right, the salinity of the water that's going out, this is out, and the salinity of the water that's coming in. And we need to find out how much water from the river is coming in. And with that, we can determine the volume of water that's going out and the volume of water that's coming in. Right? So what are the units of these volume fluxes? The V out, V salt out, V salt in. Yep. Volume per unit time, so cubic meters per second. So with that, we can define the resonance time. So those are called the Norton relations, and we can define the resonance time as the volume of the basin in cubic meters divided by the volume flux in. What are the units of this residence time? Volume over. Sorry. So what we have is cubic meters divided by cubic meters per second. So we have second. All right, so that's one definition. So you can use that one with simple measurements of or values of salinity of the water that goes out of the basin, the salinity that comes into the basin, and values of river discharge. With that, you can estimate the residence time, right? And you'll get one value in days or in months, whatever you want. There's another definition. So it'd be the time required to replace the freshwater volume in the estuary by the river flow. So in this case, it's not the water that's coming in from the ocean, but the water from the river. How long does it take for that water to be flushed out of the system? So for that, we need to we can define the residence time as the volume of fresh water in the system divided by the river discharge, cubic meters per second. Notice that again we have cubic meters divided by cubic meters per second. So the I is relatively, the river discharge is relatively easy to find out. About the volume of fresh water, how would you determine the volume of fresh water in a system? That's a little more tricky. We'll see in a minute how we can obtain a value for this volume of fresh water. But a third definition, which is essentially the same as this second one, is using the concept of freshwater fraction, which is the one that's going to help us determine the freshwater volume in the system. So in order to determine the freshwater fraction, first let's define an oceanic salinity of sigma, and the salinity at any part of the estuary will be S. So with that we can define a freshwater fraction that is given by this relationship. Salinity of the ocean minus salinity anywhere in the estuary divided by the salinity of the ocean. So what range of values can that F take? 0 to 1. How?
You could have all fresh water, and so sigma to sigma would equal 1. And then S could be equal to the salt water, obviously, so there could be 1 that's going from 10 to 0.
Very good. Everybody understood that, right? No. Excellent. Well, what Matt said was that if S equals 0, the salinity in the estuary equals 0, it means that it's covered by fresh water completely, right? And if you look at this ratio, if salinity equals 0, then the ratio is going to be equals 1. So it means that there's all fresh water. When F equals 1, it's all fresh water. And what happens if the salinity in the estuary equals the salinity of the ocean? Then we have that the numerator becomes 0, in which case the freshwater fraction will be 0. So that means that there's no fresh water in the system. It's that the system is occupied entirely by salty water. So that's the range of values that you can get. A relatively easy parameter to understand. Not so easy to determine though, but it can be sort of easy. But you need to make measurements. How do you do that? Then the freshwater volume in the system is the integral of the freshwater fraction in the system throughout the volume of the entire system. Or you can approximate it by an average freshwater fraction of the system, multiplied times the volume of the system. Can you imagine that this is a relatively easy calculation to do? And you might not even need to make measurements. All you need to know is the volume of the system, of the estuary, and this freshwater fraction. How would you determine it? That average freshwater fraction. Let's say for St. Andrew Bay, how would you determine an average freshwater fraction? Yes? that's a good way of doing it. Taking the average salinity, using the salinity at each place where we measured, and then calculate the freshwater fraction with that salinity, and then an average freshwater fraction. Or you can use the salinity in the middle of the estuary. So, for example, when we were out there, do you have any idea? Have you seen any of the data that we collected in St. Andrew, for those of you who were there? The values of salinity that we measured in St. Andrew Bay? No idea. So it's around 33, and the oceanic salinity is around 35. So from that you can see that the freshwater fraction would be around 2/35. So that would be the freshwater fraction. An average freshwater fraction. So, and then with that average freshwater fraction, you can calculate the residence time of the system, multiplying the freshwater fraction times the volume of the system, dividing it by the river discharge. Okay, so keep in mind these definitions here, because we're going to keep coming back to them throughout, that we're using this freshwater fraction to define the residence time. Okay, so as we had mentioned, that freshwater fraction, the average freshwater fraction, could be obtained from the salinity between the head and the mouth of the system. So now let's look at a different way of calculating residence time. Notice that I keep saying residence time, and over there it's written flushing time, so it's the same. Well, I see them as the same. Some people don't see them as the same. So it's all a matter of semantics. What you mean when you say residence time versus what you mean when you say flushing time. Because you can mean any of the definitions that I've used so far to distinguish between residence and flushing time. They did that in a paper that I referred at the end. So it's a matter of your taste and how you want to define what you say. Okay, so now let's look at how would tides, how efficient would tides be to flush a system. And for that you use something that's called the tidal prism method. So for that you assume that the tides bring oceanic water into the estuary during flood, and that volume of oceanic water, which we're going to call V sub P, or the tidal prism, is equal to the difference between high water and low water, and that's multiplied times the surface area of the estuary. So that's what's called the tidal prism in an estuary. So that gives you an idea of how efficient the system will be to flush itself. So the greater the tidal range, the larger the tidal prism. So again, the tidal prism is a volume, and it's simply have a diagram here. It's simply the difference between high water and low water multiplied times the cross-sectional area. Not so cross-sectional, the surface area, the horizontal surface area of the estuary. So there it is, the definition. Okay? So for this tidal prism method, what we do is that we assume that there are no variations of depth, as you see in this diagram here. No variations of depth along the estuary. So in other words, that's a short estuary. I don't know what that symbol means. It came from the translation, from Korean translation. And also we assume that over a full tidal cycle, this tidal prism is entirely mixed with the fresh water that comes in from the river. So if you can think of this has to be a very small estuary where all the water that comes in during flood mixes with the fresh water that's coming from the river, and that mixture is flushed out. So the entire volume of mixed water is removed from the estuary during ebb. And on the next flood, the process is repeated with seawater of oceanic salinity entering the estuary. So the water going in has oceanic salinity, and the water going out has a mixed salinity that we're going to call S hat. That's a mixed salinity. Okay, so we can calculate what that average salinity is, or the salinity of the mixed water at high tide is given by the following relationship. we can see that these two are equivalent expressions because we have that the tidal prism times the salinity of the ocean has to be equal to the tidal prism plus the river volume times the salinity. And I think this should be S hat right here. This over here, where's my, this should be S hat. This one, same as this one. Okay. So again, this is the let's call it the salt flux coming in during flood, and that's the salt flux going out. So this would be this salt balance. So you can solve for S hat here, which is this one, and you can see that it's S hat equals this over that, as represented here. So you can see that the average salinity, or the salinity of the mixed water, is a fraction of the oceanic salinity. You can see from this ratio. That ratio is the one that gives you the fraction. So look at that ratio. It's the tidal prism divided by the tidal prism plus the river volume. So what happens? What's going to happen if the tidal prism is much greater, just conceptually, without looking at that ratio first? Conceptually, let's see what happens if the tidal prism is much greater than the river volume. What's going to happen to the salinity that's going out? Is it going to be similar to the salinity of the ocean, or is it going to be zero? So in this case, there's going to be very little fresh water volume coming in, so the salinity that comes in is almost the same as the salinity that goes out. So what that means is that if this is much greater than that one, then this ratio is going to be equal to 1, right? So that makes sense that the salinity of the mixed water will be equal to the oceanic salinity. And let's go to the other extreme case. What happens if you have a small tidal range, that is, you have a small tidal prism, and you have a lot of fresh water coming in? What's going to happen? Well, conceptually, what happens? The salinity will decrease dramatically, right? Approaching the salinity of the water that comes in from the river, so close to zero. So if you see here, if V sub R is much greater than V sub P, it means that the denominator will be very large, so this ratio will tend to 0. So this S hat will tend to 0, right? So that's what it says here. That's what's supposed to say there. Yeah. So now you can use this average salinity of the mixed water to calculate the mean freshwater fraction through that relationship there. So notice that this ratio is the same as 1 minus S hat over sigma. And S hat over sigma, if you look up here, S hat over sigma equals V sub P divided by V sub P plus V sub R. So that's what it's right here. Right? And then you have here a difference of fractions. So you use a common denominator there, and you get that. So the bottom line is that the mean freshwater fraction equals this ratio, the ratio of the freshwater volume divided by the sum of the freshwater volume plus the tidal prism. So again, we're going to use this relationship sometime, I guess, in the following slide. But so you can see also that for a freshwater fraction, you don't need to measure salinity. If you can determine these variables here without measuring salinity. So, and this concept of freshwater fraction includes both river and tidal effects. So remember, we're trying to come up with a definition of flushing time from the tidal, from tide. So these freshwater fraction definition already includes the effects of river and tidal effects. Okay. So again, we used the previous definition for freshwater fraction, and using the definition that residence time equals this relationship, we have here that the river discharge equals the volume of fresh water divided by time, and this capital T will be a period, a time period that we'll define as the tidal period. So we'll call T the tidal period, which is the characteristic period of tidal exchange. So we can redefine this river discharge as a function of the freshwater volume and the tidal period. And we have that from the previous slide that this average freshwater fraction is given by this, the ratio of these two volumes, right? And multiplied times the volume of the basin divided by ER over T. So notice that we have here V sub R, this V sub R cancels out with that. And then this T, the tidal period, goes to the numerator. So we have VT. It doesn't mean Virginia Tech, but it means, what does it mean here? The volume of the basin times the tidal period divided by the sum of the volume of the tidal prism times the freshwater volume. So that's a definition of the flushing time as a function of the tidal prism. Because we have the tidal prism here, we have the tidal period, we have the freshwater volume, and we have the volume of the entire basin. So there it is. It's the same thing there. So notice that if the volume of the system is much greater than the tidal prism plus the river, the freshwater content in the system, then this ratio will be very large. So the flushing time would mean that it would take a lot of tidal cycles to flush the system. Notice that, and we'll mention this again. This definition of residence time or flushing time, this definition will give you a different value than definition number 1 or number 2 or number 3. So this takes into account the tidal prism. The others don't. Right? You see the tidal prism over there is the V sub P, and also the tidal period. So typically, most of the times, or maybe almost always, you'll get that the estimate for residence time using this approach will be, what do you think, shorter or longer than with the previous method? Good guess. Why do you say shorter?
Because it takes into account tidal.
That's right. It takes into account the tidal flushing of the system. Is that what it says here? No. Okay, so that's one approach. So that's why at the beginning of the class I said, well, you can give an answer, but you don't know which one. I don't know how comfortable you'll feel with the answer. But we're not done yet. There are other ways of determining. The particular drawbacks of this approach is that we assume that there is complete mixing from the head to the mouth of the estuary. So this shortens this flushing time relative to the real flushing time of the system. And also it will give you a shorter time than the other three estimates that we've talked about. This doesn't take into account atmospheric forcing. And we assume that the water coming into the estuary with every tidal cycle it has oceanic salinity. And we know that that's probably not the case, right? Because with every ebb, after every ebb, some of that water that ebbed out of the estuary will come back in. So there's a big complication for these calculations of residence time. Part of that water that was flushed out during F will come back in. We don't know what fraction, really. It's going to change from system to system. It's going to change depending on meteorological conditions, whether the wind takes it away from the mouth or brings it back in. So that's one big drawback, an important drawback. Right? In reality, we won't have new oceanic salinity coming in with every flood. So as I just mentioned before, this approach, this calculation of residence time should give you values that are smaller than the approaches used in 1, 2, and 3, that is using the steady state approach. Okay, so how do we overcome this? We have ways of overcoming it, and we'll talk about that in a minute. The way you do it is by compartmentalizing the estuary in segments where you can assume that in those segments you have full mixing and that the bathymetry is flat, so that's a more reasonable approach maybe. But before we get there, let's talk briefly about flushing rate. What would you think is the difference between flushing rate and flushing time is? What's the difference between time and rate? So time involves time, but rate involves a change in time, right? Change with respect to time. So the flushing rate is really the inverse of the flushing time, simply the inverse. So the flushing rate is the rate at which the total volume of the estuary is exchanged. So for a short residence time, a system that has a short residence time, it means that it has a high flushing rate. Very good. Means that you're paying attention, means that you're awake. So we can use some of the definitions before to say that the flushing rate equals the volume of the system divided by the residence time, or the river discharge divided by the freshwater fraction, the average freshwater fraction in the system. And remember that if we have that the residence time obtained from the tidal prism method is given by this relationship, we use that to determine the flushing rate produced by the tidal prism. So we have volume divided by the residence time, so it would be the inverse of this. So it's the volume of the tidal prism plus the freshwater volume divided by the tidal period. That's the flushing rate. And then you can also use it, well, yeah, as mentioned before, this flushing rate also, the calculated flushing rate with this approach will be larger than the flushing rate obtained with this approach. Just like the residence time is shorter with a tidal prism than using this T. So if you release a dye or any suspended material or any chemical with a concentration C, where the concentration is given in mass percentage, that is, it doesn't have units, it's just a fraction, that is released at a constant rate in kilograms per second, then the residence time of that concentration C is given by this expression: concentration times density of the water times the volume divided by the discharge rate. And the flushing time is the inverse of this, divided by the volume divided by this one. So that's why the volume disappears. So you have the discharge rate divided by the concentration times the density of the water. That's the flushing rate of, so you can calculate flushing rates anywhere that you can take, in your bathtub or in smaller basins. All right, so let's go back to looking at how we can use this residence time using the tidal prism approach in sections or segments of estuaries where we can assume that there's complete mixing over smaller lengths of the estuary. So we will modify the tidal prism method dividing the estuary into segments over which mixing takes place, instead of assuming that there is complete mixing over the length of the estuary during each tidal cycle. So we can assume that in those segments that might be as long as a tidal excursion, you're going to have full mixing. So the length of each segment could be determined again by the tidal excursion. That's how you determine the tidal excursion. What do you think each one of these variables represent? We're talking about tidal excursion. U naught would be the tidal current amplitude. T is the tidal period. And pi is March 14. 314. Right? Somebody, my middle school son made that joke the other day. So. No, actually, no, they had to do something for school, a cake, a pie on 314. So I thought it was pretty clever. I had to do a pie that had 3.314 on March 14. So the teacher was thinking, I think. All right, so each segment, we will assume that each segment looks something like this, that it has a volume V sub I and a tidal prism. This would be the tidal prism volume of each segment. We will call it P sub I. So that's the intertidal volume segment, or the tidal prism plus any freshwater volume that's in there. So the V sub I would be the volume at low water. So what we have is at the very landward end where we decide to define the upstream limit of our estuary. The low tide volume will be V sub naught, and the P sub I, this segment, will be the volume of fresh water from the river, and this is averaged over a tidal cycle. So the volume provided by the river discharge. And for the succeeding segments, what we will assume is that the high tide volume of the landward section or the landward segment, so this volume will be equal to the volume of the seaward adjacent segment at low tide. So we will assume that again that this volume is the same as that volume, as we partition our estuary in different segments. Remember, we're assuming that there's complete mixing every tidal cycle in this volume, and same as this volume, and so on. So the assumption that this volume equals to that volume like that, as we have drawn it here, implies that the tidal excursion decreases landward. And why? Because this is shorter than this one. So the tidal excursion decreases landward. So as we move seaward, this segment becomes fatter or longer because the tidal excursion is decreasing from here to here. Or alternatively, that the channel gets narrower. And this is reasonable, not to every system, but to a lot of systems, that the tidal excursion, that is the tidal currents, decrease as you go further up the estuary. Or alternatively, that the coastline of the estuary is converging. So again, in most systems this is true, but not in all of them. So we have, in general, that the volume of the N segment, this volume, is going to be equal to the volume at low water of the previous segment plus the tidal prism. So what we can write in general is that for the first segment after the river segment, we have that the volume of the river plus this is the tidal prism in the segment. So in the segment of the river, so this would be the fresh water from the river. And then the next segment would be the volume, the first segment, V sub 1, plus the tidal prism in that segment. But V sub 1 is V naught plus P naught. So you have V sub naught, V sub 0, P sub 0 plus P sub 1. And so on. The next segment will be this one, which is right there, plus P2. So in general, any segment will be as given by this expression up here. It's going to be equal to V sub 0, which is the volume of the river segment, plus the sum of all the tidal prism volumes, which is given by this. So in other words, there's the freshwater volume, the river segment volume plus the freshwater volume plus the sum of all the intertidal, the tidal prism segments. So again, you can use these volumes to calculate the residence time at each one of these segments. So you calculate at each segment, you calculate the residence time, and in this way you'll get a spatially variable residence time for the system. You can also use a new concept which we'll call the exchange ratio, which is the ratio between intertidal volume and the high tide volume. So the ratio between these and that. So in other words, the ratio between the tidal prism and the high tide volume. That's the exchange ratio. So in a tidal flat, what's going to happen is that the exchange ratio is going to be equal to 0 because the tidal volume will go to 0. If it dries out, think of a tidal flat where the tide comes up, so you have a volume, and then it goes out, so that would be the piece of n. The volume of water that comes in and out, that's a piece of n, but the V sub n will be 0. There's no water there at low tide, so the V sub n equals 0. So in a tidal flat, V sub n equals 0 and the exchange ratio equals 1. So in a segment of a tidal flat, the exchange ratio is perfect. With every tidal cycle, over that tidal flat, the water gets exchanged every tidal cycle. And using the concept of residence time now, that's given by this expression, remember this is the definition of residence time for the tidal prism method. And we could use these for each one of these segments to determine a residence time for each segment. So using that definition and using the fact that V over Vp sub V R, which represents the volume of the basin plus divided by the tidal prism plus the freshwater volume, and this is also equivalent to the high tide volume here divided by the modified tidal prism. So in other words, this ratio can be written as this ratio, which is the inverse of the exchange ratio. So from these, you can get the residence time at each one of the segments using the exchange ratio. Because you have here where you have this equals 1 over Rn. So if you move, how is that? Yeah, so this thing that we have here is 1 over Rn. So T sub T equals capital T over Rn, right? Because this whole thing, V over Vp plus Vr equals 1 over Rn, as we see here. V over Vp plus Vr equals 1 over Rn. So again, we can calculate the residence time at each one of the segments with the tidal period and the exchange ratio. And again, the exchange ratio, as we had said before, depends on the tidal prism divided by the high tide volume. So again, this is a geometric calculation. You don't need to measure salinity. And this, at each one of the segments, you can subdivide your estuary by segments, and you get a T sub n that's spatially dependent. So that's useful. And then we can determine the accumulated fresh water in each volume segment, which is this, the accumulated fresh water is the residence time divided multiplied times the river discharge. So notice that this is in time, and this is in length, cubic length over time. So we get a volume, and that's obtained from this residence time, T sub n equals the tidal period divided by the exchange ratio, and then this river discharge equals the freshwater volume divided by the tidal period. So notice we can eliminate this tidal period in such a way that the fresh water accumulated in each one of the segments equals the volume of fresh water divided by the exchange ratio. And finally, the salinity, the average salinity equals this fresh water accumulated, the volume of fresh water accumulated divided by the volume of each segment, which is the same as 1 minus the fresh water fraction at each segment multiplied times the salinity of the ocean. So if you have salinity measurements, you can use this approach to determine the salinity, the average salinity at each one of the segments too, and also the freshwater fraction. So alternatively, you can calculate the freshwater fraction at each one of the segments and get an estimate of residence time there. So there's this nice paper where they talk about all these approaches, and they actually make the semantic difference between flushing time and residence time and flushing rate. So anyway, you can use any of those approaches to give an answer to residence time. But still, that I don't like any of those, but you might like any of those. Why do I say that? Because depending on where you are in the estuary, a particle, like you said at the beginning, a water particle or a pollutant, depending on where you are, will take different time, right? And it depends on whether you release it at low tide or at high tide. It'll take different time to get out of the estuary of the system. So it's a simple question, but there's no simple answer for that. And probably the best approach to determining residence time is determining it from particle tracking in numerical model. Like given in this example in an estuary in Portugal. So we have here residence time in days following particles in a numerical model. So if you release a particle here, you see that it's going to take around 250 days to be flushed out of the system. If you release a particle here, it's going to take only 1 day or 2. So depending on where you are in the estuary, if you release it here, it's going to take around between 20 and 50 days, as you see in the scale. So again, to me, this is a better answer. When somebody asks you what the residence time of the system, if you give a map like this, then that gives you a better idea, I think, of how efficient the system is to flush itself. We see here that it's not very efficient here, and it makes sense that it's most efficient here near the mouth. That's the one with the closest contact with the ocean. So one value, in my book, one value doesn't work. So one value answer don't work. But that's what they want to hear. Many times that's what they want to hear. So I think it is our job to tell people, okay, I'll give you one number, but you have to be careful with this number and you have to go through the explanation of why it might not be an appropriate number. There's another interesting example here in that. This is taken from, if we go back from the website of Tomsha, you go to that web page, you'll find a little more discussion on flushing times. But I took this example from his website, and this is in an estimate of the residence time in a nice atoll lagoon here in the middle of the Pacific Ocean. That's where, in the Polynesia, where this lagoon was used for nuclear tests. And the residence time is given in this figure, but it's determined from numerical models. Here's the bathymetry. So it's an atoll lagoon, so there's coral reef all around here. It only has one opening, direct opening. So you can have some waves overtopping the coral reefs there. or the barrier. It's an atoll, so it's mostly exposed most of the time. So only with high waves would you have some water coming in the lagoon. So the main flushing is through this channel. Yeah. And so the bathymetry is here. You can see that there's a deep basin here of close to 40 to more than 50 meters here. And it pretty much follows the shape of the atoll, the bathymetry does. And here's the flow pattern obtained from a numerical simulation. These are the streamlines, and the zero streamline is like that, is the pink one. The yellow streamlines mean that the flow is counterclockwise or anti-clockwise. Yeah. So right here near the channel, the water goes counterclockwise. It recirculates in a counterclockwise fashion. And around these streamlines, the water goes clockwise. So the general circulation in the lagoon is like that. If you follow those streamlines. And you can see, this is the bottom line, the residence time in the lagoon. And you can see quite dramatic differences of maybe 10 days, that yellow one, or 20 days. And here, which would be the part of the lagoon most prone to pollution, or we have more than 120 days, so half a year, maybe half a year here to flush that part of the lagoon. And you can see here that almost half of the lagoon takes more than 100 days. So that's not a very good place to do nuclear tests, because the nuclear traces will stay there for a while. I don't know if it's been flushed completely by now, but there might be still some concerns here. Okay, so are there any questions? So the bottom line here of today's lecture, I think, is that when somebody asks you what the residence time is, if you can produce a map like that, or the previous one, I think that's the best answer you can give. Also, you'll find out that this map will change depending, I insist, depending on whether you look at a release during low tide or during high tide or in the middle of the tide. It becomes very complicated how things will be different whether you release at different phases of the tidal cycle. So those are some things to keep in mind. And I know it's a very complicated aspect, and you don't want to be overly complicated when somebody asks you a simple question. But so you have to be aware of this. Again, you can give a simple answer by using any of the initial approaches and say, but look, you have to be careful with that number because of this and that. Because if you can generate a map like this, then that's what you should give as an answer. All right? Any questions? Let's take a quick break.